Howdy, and welcome back. So let's go ahead and get started with the discussion on the standard libraries vector. So with all of these, they are going to be library facilities, so we will have to include them in our applications, similar to what we had to do when we were interested in using IO streams with pound include IO stream. Here, if we'd like to use a vector in our program, it will be pound include vector. So a standard library vector is going to be a sequence of elements of homogeneous type that can be accessed by an index into the vector. This will be reminiscent of arrays that you have worked with in your past programming languages, with the caveat that we'll see these vectors can grow to an arbitrary size. So given some vector named V, and assuming it has already been populated with data, you can think about representing this object as follows. We're going to have some sort of mechanism to actually store its size. So unlike primitive arrays in C++, which we will eventually get to, that are unaware of their size, a vector does know its size, and we'll have the ability to ask it what it is through the member function size. Likewise, a vector is going to store an array, which will house your data. The vector's type is going to be responsible for maintaining this array behind the scenes. So in some languages, you might have to think about what happens if I allocate an array of some size and I exceed that size. What do I do? Here, the vector will handle all of that for you. So you have the illusion of kind of an infinite, an ability to collect an infinite number of objects into this structure. Obviously, memory within the limits of the memory allocated to your program. So we're just starting this out. We're saying that V has the numbers of 1, 1, 2, 3, 5. So it's going to be a size of 5 objects. The first element is going to live in V at index 0. So everything that we're going to be working with in C++ here is going to be 0 index. And we'll precisely see why that is when we begin talking about arrays. But for now, let's just focus on the vector. A vector doesn't simply store its elements, as we noted, but it's also going to store its size. So looking here, in V's kind of array that it's maintaining, the first value that we're storing will reside at location 0, which we'd be able to access using subscripting. So we could say, hey, V, give me the object at your array's location 0. And that would give us this object back. So we could do things like V of 0 equals 3 to assign it a new value. If we wanted to access the second element, it lives at location 1, and so on and so forth. So we can make a vector held a collection of integers, such as that on the previous slide, by introducing that vector through this declaration. We can say that we would like a standard library vector. We would like it to store int type of elements. So each element within this vector will be of type integer. And then we'll go ahead and provide it a name, in this case, V. Obviously, in your program, you're going to want to use more descriptive names, but to keep it short and sweet on these slides, we're going with V. Next, we'll see that this is an initializer list, but we can upfront specify what we would like this vector's initial values to take on. So in this case, we get in a vector of V. It has size of 1, 2, 3, 4, 5, and it's owning this array of 5 elements. So that's what we've essentially set up when this line of code becomes executed. We can hold objects of different types in this vector as long as the objects that we put into it are homogeneous. So in this case, you could specify the vector, the type of the vector's elements, by just changing up what's presenting between the angle brackets there. If we wanted a vector of doubles, we would change the int to, in this case, double. If we wanted a vector of standard library strings, which we'll get into shortly, we would just say we want it to be a standard library string. So this holds. So you can store objects of the type you're interested in, as long as each element within the vector is of that type. So that's one way to declare a vector in a program. There's other ways to do so as well. We could have also declared a vector of some given size without specifying the values of its element. So here's an empty vector of doubles with a given size of 4. So this statement here creates a vector of size 4, and it's going to own an array that can hold 4 elements. The elements are going to be given a default value according to the type of the element in this case. We could have specified this, but the default for double is going to be 0.0. So that's how each of the elements within V are initialized in this case. Alternatively, if we wanted to have them initialized to a different value, we would specify that. So we'd have size, comma, default value in our declaration. This is just you could think about it as kind of a parameter list directly following the identifier. And again, when we get to classes, you'll see exactly how this mechanism is bringing this vector to life. But for right now, just take the syntax at face value and use it accordingly. We'll get into all the details. Don't worry about that. Just worry about, at least right now, just worry about an ability to use this type and create objects thereof. So here, I mean, it looks pretty much identical to what we already had. In this case, 4. Each is going to start out is initialized with 1.0. We could have put 5 there, 10, whatever. So we've created these vectors. How do we go about accessing their elements? Well, we can access them by using the vector's name followed by the subscript operator. So in this case, we can say v of 2 to get us the element residing at index 2, or the third element within this vector. So this is going to provide access to this integer object here. If we wanted to assign to that object in our collection, we simply write an assignment statement. That would change our vector to go from 1, 1, 2, 3, 5 to 1, 1, 10, 3, 5. With, again, only that element being changed, because that's the one we requested to assign to. So subscripting is one way how we can introduce or interact with the different elements within this collection. However, we're always going to encourage you to use this at notation here. You'll get it as we get into classes. You'll understand that this is a member function, and we'll see here that it is defined slightly different than subscripting is for a vector. If we write v.at 2, we get exactly the same back. This is equivalent. If we write v.at 2's equal to 10, same thing, equivalent. However, if we write v.at 100, which is not within the range of this vector, it's not a valid index into it, we're going to get an error. It's going to be very clear to us, and if you're familiar with exceptions, it's essentially an exceptions being thrown in this case. But it will allow us an ability to, once we learn about error handling, how to gracefully deal with conditions such as this. We're attempting to access elements that are outside the range of our container. Now, if I wrote v of 100 up here, no error is going to be produced. So that would be a very difficult error to kind of catch. And right now, I mean, that's, 100's probably, you're going, yeah, when am I going to do that? Where this really begins occurring is when you're off by 1. So right here we have valid IDXs of 1, 2, or 0, 1, 2, 3, 4. A lot of times we'll forget that it's 0 index, and this could be a consequence of how we're writing a conditional on a loop as we're iterating through this collection, say. And if you write something like v of 5, you're essentially accessing, in this case, I need to work on drawing these things. That element, which is one past the last element in the collection, in C++ will allow you to attempt to access that. Had we wrote v.at 5, we would have easily caught that and we wouldn't have been operating outside the range of our vector. Okay, so since a vector knows its size, we can essentially iterate through it and operate on each of the elements, look at each of the elements, do whatever we want to each of the elements within this collection. So to begin iterating through, we could write a for statement that visits each element and accesses them by indexing into them. So size t is essentially the maximum possible size that this vector could be, the maximum possible number of elements that it could contain, and that could exceed an integer or an unsigned integer. So in the event that we were dealing with massive vectors, always kind of using size t as the type of the control variable is going to be helpful, because if we are attempting to access into the vector at a very large index, size t will be able to store that value for us. We initialize it with 0, which means at this point, IDX is right there. 5. We check whether or not we are outside the range of this vector. And remember, size here is going to be 5. However, the valid indexes are here. So when we're here, we want to terminate the loop and not execute the actual body of the loop. So 0 is going to be less than the vector size in this condition. We'll jump into the body of our loop. And here, all I'm doing is outing the value at that index. So here, first time through, the output's 1. We go on up, we hit this expression here, we increment IDX, index by 1. We hit the body because 1 will be less than the size. We output 1 again, which is this element. Continue this process, 2, 3, 5. And then at this point, I is going to be 5. We jump up here. We go, is 5 less than 5? No, it's equal to it. So we can pick up directly after it, and the loop terminates. So that's one type of way to iterate through this. Alternatively, if we know we'd like to visit every element in this sequence, we can use the range-based for loop, which is going to be reminiscent of a for each statement provided to you in probably other languages. You can't use this for everything. For instance, you have to be applying it to some sort of sequence of elements that have a well-defined starting point in operation to get from one element to the next in the sequence, and then also the means of determining whether or not you have iterated through and visited each element within the sequence. We'll get into how that is implemented a little bit later, but for the use of the range-based for loop, we can definitely use a vector in it. So we're saying here, for each integer val of vect, so essentially on the first time through this iteration, it will know that val is going to be essentially whatever is stored in the 0th index. That's what value val will take on the first iteration. Second, it will take on the value of 1 because that is what resides at the next element in this sequence of elements. Then 2, then 3, then 5, and then it knows to stop once we're one past the last element. This equivalently would print 1, 1, 2, 3, 5. So here's a cool feature about a vector. Let's say we have some big collection of data. We haven't talked about files, but you could imagine that maybe I provide you with a file and I say, hey, read in all the, read all the data points within this file. And you could go, okay, well, does it specify a size up front? If it doesn't, how do I know, like, what should the size be? I can't read from it. So what we're going to see here is that the vector is going to allow us to essentially grow from empty to some sort of size that is able to handle all of the elements that we might wish to put into it, again, bearing memory constraints for our program. So just to reemphasize, this is particularly helpful when reading an unknown quality of data into our program. The key behavior that's going to allow us to do this is going to be pushback. So we'll be able to ask a vector, hey, V, push back this value, and it will simply add it or append it to the end of the vector. So how does this work? We could just make a declaration for an empty vector as such. And again, you'll kind of see what's going on behind the scenes or under the hood, however you want to view it, when we get into classes with dynamic memory. And we're not there yet, but so again, just focus on interacting with and understanding kind of what's happening at this level. And we'll get into a lower level of abstraction soon enough. So don't, we'll get there. If I were to ask VAC to push back the value of 10, what's going to happen is the size is going to increment by 1. And then the array that vector is maintaining will have the value of 10 added to it. We can see here, if we want to continue growing the vector, pushback will increment the size by 1 and append that value to 1. Because this is happening, if you write a iterative statement that's walking through each elements, in this case, we're not going to visit any elements. In this case, if we're looping based on the size of the vector, we'd visit 1. And then if we wanted to loop back after we have all of our data, again, if we're just looping on size or using a range-based for loop, it knows because the vector knows its size, we're able to visit each of the elements that are stored within it and do some sort of operation, view them, whatever it is you might like to, however it is you'd like to interact with them. So there are many things that a vector can do. So far, we have seen that a vector can tell us its size, provide us an element residing at a particular index using either the @ notation or subscripting. We can add a value to its end, effectively growing its size by 1 using the pushback behavior. There are other behaviors, things that a vector object can do, and those are going to be described in its API. If you have a moment, I'd pause this video, I'd go to this URL, and I'd look at all of the functionality that a vector has the capability of doing. There, you could ask for instance, there's, I believe, .front, which would give you the first element in the vector. There's .back, which would give you the last one. There's remove. There's a bunch of different behaviors that you can apply to objects of this type, and how to use them, the API will tell you.